we'll solve a problem based on the topic we discussed yesterday. Okay, right? Uh, no, only one equation we covered so far. So this is the only equation, correct? So IDS is equal to, right? Either you use beta into VGS minus VDH, VDS minus VDS square by 2. This is one equation where beta is K into W by L, right? And you know that the K can also be written as mu n epsilon ins, insulation layer epsilon value, epsilon naught divided by thickness of that layer, right? So any of these form you want, you can use. Is it okay? All right. Now, so the question is like this. So design the circuit shown below to get a DC voltage 9.9 volts at source terminal. All right. Also calculate the effective resistance of the channel. Okay, so this is the given circuit. There is a 10 volt power supply. This is connected to a N MOSFET, and so at say this point we are shorting this, and then say we have a resistor connecting this to ground. All right, so this is the drain terminal, this is the gate, and this is the source. And they are saying that at this point it is expected to have 9.9 volts. Let's say okay. After the class immediately. Okay. Kindly remind if you didn't get the notes, right? Because if I have a class immediately after your class, right? Most of the time I used to I forget. Fine. So this is the question, and they mentioned that assume this question actually continues. So assume V threshold is equal to -1 volts, and take the beta value is 1 milliamps per volt square. All right, so this is the question now. So from this given data, this actually is a question from old question paper. Oh, okay, so let's start answering this. So what is given? You can see that the drain voltage is given, right? So you see VD is the term connection to the voltage given to the drain terminal, that is 10 volts, right? And it says that I am supposed to get Vs, the source terminal should have a voltage of 9.9 volts, isn't it? Right, so let us calculate this now. So what is VDS? VDS is equal to VD minus Vs, difference between drain and source. This is 9. Then from this given circuit, can you tell me what is VGS? They have not given the value, but they have shown it in the circuit. So you can see when it is connected like this, I can say that the so my question was not VG, right? If I asked what is VG, then 9.9 is correct. But my question is what is VGS? Difference between gate and source, right? In that case, it has to be 0 volts. Right? This doesn't mean that VG is 0. VG is 9.9. Right? But the difference between gate to source is 0 because you see the equation, we in the ID equation, we are specifically looking at VGS, not just VG. All right. So then the given data, V threshold is given. Okay, everything we have now. Directly, let's calculate the ID, right? So data times whole square. Are you okay with this equation? Right? We know this equation, we have derived this, right? So value has been given over there. This is 1 milli, so 1 into 10 to the power minus 3 into, right? VGS is 0. V threshold is how much? It is minus 1, so 0 plus 1 whole square into just now we calculated the drain to source voltage. VDS is equal to 0.1, correct? Minus VDS square is 0.1 square divided by 2. This is equal to, yeah. So can you repeat the answer once again? Yes. 9.5 into 10 to the minus 5. Convert it into minus 6 or you write in minus 3 format, right? So I prefer writing in the milliampere, so I write 0. This becomes 0.095 because 2 you have to move the decimal point to left by 2 units, then you can convert this into minus 3. All right, so amperes, the answer is in the standard format 0.095 milliamperes. This itself can be converted into 95 into 10 to the minus 6, so that is 95 microamperes. Both are fine. Okay, let's proceed further. So you can see the question say that design the circuit. So design the circuit requires us to find out all the unknowns such as the resistor value. Correct. Now, can you suggest a method to find out the RD given in the circuit? I'll show you the circuit now. Perfect. So, correct. Given as 9.9 volts, and just now we calculated that ID is equal to 0.095 into 10 to the power minus 3. So, yes, 104.2. Can I write kilo ohms? Of the FET in the sense, right here you can see in this particular case between the drain and source I have a channel, right? So what is the resistance of this channel is what they are asking here. Okay, so now of the is equal right? So I think 63, right? The ohms, right? 1.0 kilo ohms, 0.5 kilo ohms. Absolutely perfect. All right. So just calculate this now. Design the following circuit to get a source voltage of, this is 11.85 volts. So circuit still remains same. This is 12 volts. RD. So threshold is equal to point beta was given. Okay, beta is equal to 1.6 into 10 to the minus 3 volts. Next, MOSFETs, and we try to write the equations in the saturation region. So this discussion was saturation or the Ohmic region. Now, the relationship between VDS, drain to source voltage, and the gate to source voltage is different than that of the ohmic region. Correct? In saturation region, the VDS is either greater than or equal to the VGS minus V threshold. At this point, the IR drop, in the sense the voltage drop of the channel, is equal to the effective gate to channel voltage. Whatever is the gate to channel voltage, right, it's equal, the same voltage will be dropped across the channel. That's what is the indication. Okay, so here the IR drop, in a sense the voltage drop, right, in the channel, IR drop in the channel equals to the effective gate to channel voltage. So there the current through the channel remains constant and it is no more dependent on the VDS. Okay, so because of this you see that VGS, right, will actually hold the channels width fixed, because of which VDS you further increase has no effect on the current. Correct? Yeah. Therefore, the current through the channel remains a constant, right, with respect to to VDS. All right, with respect to VDS. That means let's go back to the waveform or one here. You see here, right? The current is plotted versus VDS, right? I am changing VDS here, but my current is actually a constant, straight line. You increase VDS, no change happens with the IDS value, which is almost fixed here, right? Yeah, it actually, right? Changing VDS on IDS. So previously, as you change VDS, IDS increases, right? In this region. This was the previous case, ohmic region. But now it's a constant. Are you okay with that? Yes. So therefore, we can write the IDS in this format now. Therefore, IDS becomes equal to, now the IDS in case of a saturation region, you are going to write K times W by L into VGS minus V threshold whole square whole divided by 2. Either this equation you can use, if the K and W and L are provided, you can use this. Otherwise, if beta is given, you can use, because kw by L itself is a beta, right? So this is beta by 2 VGS minus V threshold whole square. Okay. Otherwise, if the further details are given, like oxide layer thickness, right, and the length of the channel, mobility, etc. is given, right, then you can use the following formula. That is the mobility into the capacitance of oxide layer whole divided by uh, mu Cox W by 2L into, this is VGS minus V threshold whole square. So use whichever formula you are comfortable with. Now, these are the three important equations we are going to use in case of, right, which region? Saturation region. All right. Now, yes, in any of the given circuit, if you see that the VGS minus VTH is, right, greater than the VDS, the VGS minus VTH is bigger value than the VDS. That means, right, the circuit is in the linear region, ohmic region. But if VDS is bigger than VGS minus VTH, that means it is in the saturation region. So I need to use the same equation to identify whether the given circuit is in the saturation region or the ohmic region before I apply the appropriate equation of ID. Okay, so therefore, let's write the common current equation. ID is equal to, now we know that the whole circuit, right, can be operated in three different modes, correct? So that is, in all the three modes, we'll write what are the equations of current. First mode is there is no current because the VGS is less than V threshold, and we are going to call it as the cut off region. No current because VGS is less than VTH. Then the second equation will be, this is beta times, this is VGS minus VTH. So the previous equation, if you look at that, VGS minus VTH into, I'll use another bracket inside, into VDS minus, this is VDS square divided by 2. Okay, this equation you are going to use if the VDS is less than VGS minus V threshold. So this means it is, right, ohmic region. VGS minus V threshold. This some of the textbooks will use another notation, that is they call as VD sat, which is nothing but the VGS minus VTH. They might use a different name. So instead of this, you may see a VD sat over there. Okay, VDS is lesser than VD sat, VDS is greater than VD sat, etc. All right. So that's all it is. Now let's look at the IDS versus VDS curve, right? Let's look at that curve when you operate an FET in both the regions, right? One in the resistive and one more in the uh, non-ohmic, that is saturation region. All right. So let's try to plot a graph. This is VDS versus IDS, or you can call this as the output characteristics of the MOSFET. So I'm going to plot IDS versus VDS. See, this is the output current versus output voltage when the input voltage is kept constant. All right. I'm going to keep input voltage constant. That means, so the first curve is going to be something like this. It will slightly increase from this point and then it becomes a constant. Okay, let me assume that the VGS is equal to 0.2 volts. It's a fixed voltage. Okay, and next let me assume that we increase the gate to source voltage slightly. Okay, instead of 0.42, let me assume I kept 0.4. In that case, the graph is going to look like this. So in this case, you see input voltage VGS is kept constant at 0.4 volts. Okay, further increase. Let's say that VGS I keep as say 0.8 volts, right? So V gate to source is 0.8 volts, a different value. Okay, then let's further increase. VGS is much bigger and it becomes like this. So maybe VGS is equal to 1 volt. In this graph, I can separate the regions. I can see that this is how the regions are separated, correct? So this side is something and this side is different, correct? So what is this? This is ohmic and this side is the saturation. So if the question is something like plot the output characteristics of a MOSFET, right? What do you mean by, because you just have to remember what is an output characteristics, right? So output characteristics means, I'll just write here, output characteristics is the plot of output current. What is output current in this case? Let me write that, that is IDS. Okay, versus the output voltage, that is VDS. It's not just this, when it also has to include when the input voltage, that is VGS, right, is constant. All right. So this is the practical curve that we obtain for the MOSFET. What will be the difference? I have a question. In this particular graph, right? Can you tell me whether this MOSFET is enhancement mode or depletion mode? So when I look at the graph, it's very clear that below VGS value lesser than zero point 0.2, there is no conduction, which means there is no channel. So when channel does not exist below the threshold voltage, that means this is which type of MOSFET? Means this particular channel, this particular FET is a enhancement MOSFET. Correct? Now, what is the difference that you expect in this graph if this particular FET was a say depletion type MOSFET? So in this graph, if VGS has the values from negative value coming to 0 and then becoming positive as you move, right, the VDS level to above, right, that is the case, then that will be the graph of the depletion mode MOSFET. So the next, basically the MOS transistor operation has three different regions. We know that one is cutoff, linear, and the saturation. In because of a MOSFET being operated in several regions, right? There are some practical effects which are neglected when we wrote the equation for IDS. So just now I wrote a combined equation for IDS, right? So this one, ID is equal to 0, or the one equation for ohmic and one more equation for saturation. But when we wrote this, actually we neglected the practical effects, right? Particularly in the linear and the saturation region, right, we actually, right, have neglected some of the physical or the practical effects, right? So those practical effects are called as non-ideal effect. Ideal means it's not practical. You just ideally you think about something, okay, that's why you wrote an equation. Now we come to the uh, practical situation scenario where we need to add few more terms, right, to the equations, considering the non-ideal or the practical situation. So the first one is called as, first effect is called as the velocity saturation, right? Normally there is a drifting velocity for any charge carrier. For example, electron will drift from the source to drain with a velocity called as drift velocity, right? So due to the carrier drift velocity, right, the current increases linearly with the electric field, right? Yeah. Whenever you apply electric field and you keep increasing the electric field, the velocity of electrons keeps on increasing between whenever they move between the source and the drain. Right, that is ideal case. Drift velocity to increase, right, and hence the current also should increase with the electric field between the source and drain. Okay, but you see, as the speed of electrons increase, normally there is more and more collision between the electrons. After they collide, their actual velocity will be reduced. There is always a saturation, like, okay, this is the maximum velocity they can achieve whenever they move from source to drain under the given value of the electric field. Even after that, even if you increase the electric field, there is no effect on electrons velocity. This is because they have saturated, so they collide. Even after that, if you increase the electric field, they simply keep colliding, the total velocity will not increase, right? So that is what is called as the velocity saturation. So see, this point we never considered, we just told that when we derived, okay, as you keep increasing the Vg, right, we are expecting more and more field to come and velocity should increase. This is what we discussed, correct? So let's write what is velocity saturation now. So ideally, right, when the electric field is increased, right, the drift velocity of electrons, and hence the current, right, must be increased. Correct. So when electric field is increased, we are expecting the drift velocity of electrons should increase, and because of that, even the current should increase. Correct. Should be increased, right? This is the ideal case, but now we come to the practical case, right? In practice, what happens, right? The drift velocity, we can say, rolls off. In the sense, initially it will increase, but later on it actually becomes a constant value, right? Rolls off due to, no, they start colliding after a certain value, right? See, initially lower value of velocity, everybody has time to reach to the destination, but when you increase this by a huge value velocity, right, they will collide with each other because of the high velocity. The space is very less, right? Inside the region has very less space, so high speed means they will collide with each other, so there is a scattering. Okay, so rolls off due to the carrier uh, collisions and scattering, right? uh, it will roll, the velocity rolls off because of this, and hence saturates, saturates to what is called as VSAT. This could be the some maximum velocity it can attain. All right, so let's look at a graph indicating this event. So this is important whenever a question comes on the what is called as the VDSAT or non-ideal effects, right? First you write the concept of the carrier velocity saturation, right? So it looks like this. So if you have it start like this, initially we will observe increase in this, but later on you will see that it is going to saturate, right? So horizontal field is the E, electric field, right? It's the magnitude of electric field, and this will be the velocity of carriers, right? So you see that ultimately it's going to saturate at a given value. It will come and touch that point ultimately, right? So that is V sat. All right. So because of this, we have of this effect. You can see that the IDS can be updated as this. So this is AC aux dW into VGS minus V threshold into, you write a, because of this VSAT, we have next effect coming up, that is what is called as the mobility degradation. So the mobility degradation, in the sense, when you see that there is a strong electrical field that is existing inside the channel because of a large amount of gate to source voltage, right? Right? So carriers will scatter. The same point which we have written earlier. So I just write in short so that when you read, you understand this. Okay. High E, right, indicating high electric field due to high value of VGS, right? This implies there is scattering. So this will reduce the mobility. That's all. Reduction in mobility of E. I'll just write E because it is electrons. Right. Then after this, I'll directly go to the next one. Next effect. It is called as the channel equation corresponding to the mobility degradation has already been taken care in the previous case. Okay. So where we wrote the VSAT, right? So their mobility is reduced by changing the velocity. Okay. Effect is so you see, I'll go back to a specific diagram which we wrote in the previous class comparing, right? You see that original channel length was from here till here, right? This was the original channel length. But when this entered into the saturation region and you further increase the VDS, right? You see that the channel length keeps on reducing and now it has reached only till here, right? So this is what is called as the channel length modulation, right? Because of this, the effective length of the channel reduces. Okay, so this I'll just write quickly about this. So when you reverse bias the PN junction of drain and the body, correct? Reverse biased PN junction of drain and the body of FET forms what? Forms a thicker, it's a reverse bias, so you have a thick depletion region, correct? Right. That region, let's call that as depletion region, say LD. L is the length of the depletion region, right? LD. Now you see that as you increase VD, the LD increases as VDS increases. This is because reverse bias voltage is increasing, right? So this implies the channel length becomes equal to original length minus LD, right? So that means depending upon what is the value of VGS and VDS, right? You see that there is a channel length modulation factor coming into picture, right? So this channel, this process is called as channel length modulation, right? There is a change in the length of the channel. Okay, since this change in the length of the channel depends upon VDS, we directly write the equation as IDS is equal to, this is beta times VGS minus V threshold the whole square divided by 2. This is the original equation into 1 plus lambda times VDS. So here the lambda is what is called as channel length modulation factor. Okay, so using this factor you can decide, right, how much IDS varies when there is a channel length modulation determined by a value called lambda. Yeah. Right, so this is very important parameter whenever it comes to the designing of a practical circuit for a design engineer. Yeah. Okay, so these are the different effects, right? Three things we covered. There is one more coming up. One more, sorry. I think two more main things coming up. One is body effect. One is punch through effect. Okay, those two things are left, right?